Young's slits experiment. This experiment provides evidence for the wave nature of light. It requires two coherent light sources. This is because it works by the interference of the two light sources, and by coherent we mean there must be a constant phase difference. This could be zero. At A level it almost certainly will be zero. They must have the same frequency and therefore the same wavelength, and there must be approximately the same amplitude. This is so that when they meet 180 degrees out of phase, they will destructively interfere. Two independent light sources would not have a constant phase difference and so would not be coherent. What we use is a monochromatic light source, such as a sodium lamp. Monochromatic literally means one colour and therefore one wavelength. We pass the light through a single slit before then passing it through double slits. These two slits then provide our two coherent light sources. Along here we then need a screen to capture the light on. The waves will pass through something like this. And around about this point the two coherent light sources will cross. We will get interference in this region here where the two light sources come together. Now it's more common to use a laser which covers the two slits, providing the coherent light source. This diagram is very much not to scale. The gap here between the slits would typically be around about 0.5 millimeter, and the distance from the slits to the screen would be around 6 meters. As we move along the screen, we alternately get regions where the two waves will meet 180 degrees out of phase and destructively interfere, leading to a dark band, completely in phase and constructively interfere, leading to a bright band, and so on. What we see on the screen is a region of dark, bright bands. The eye is not sensitive enough to notice the shading as we go from dark to bright, and we only see distinctive stripes. Now to look at how this comes about. For clarity, I've just shown the two slits and the screen. If we look at light reaching this point here, it will come from the top slit and from the bottom slit. The distance is further from the bottom slit than the top slit, as represented by this distance here. If that distance is a complete number of wavelengths, the two waves here will meet in phase, constructively interfere, and produce a bright fringe. A little bit further down, the path difference will be slightly less. If this is now an odd number of half wavelengths, crest will meet trough, leading to destructive interference and a dark fringe. Further down still, we will end up with a complete number of wavelengths path difference again, leading to constructive interference and another bright fringe, and so on. Just to recap, we get a bright fringe where there are a complete number of wavelengths path difference from the top slit to the bottom slit, leading to constructive interference. We get a dark fringe where there is an odd number of half wavelengths path difference, leading to destructive interference. If we assign some symbols to the distances involved, we will call the slit separation S, we will call the fringe separation W, and the distance from slits to screen D. We then find that the fringe spacing W is equal to the wavelength of the light lambda times the distance from slits to screen D divided by the slit separation S. You are not expected to derive this equation, but you would be expected to be able to use it to find any of the quantities in the equation. Of course, as when measuring any small distance, it is much better to measure several and divide by the number measured. In this case, if we were to measure from here to here, this would be 1, 2, 3 fringe spacings. In reality, the fringe spacing would be very small, and you could measure many more than 3, dividing by the number measured. Of course, we experience two-source interference whenever two coherent waves meet. For example, with sound, we can have a signal generator connected to two speakers. If we go along here, we would find the sound would be loud, then softer, loud, then soft, loud, then soft, and so on. The speakers are like the slits in the previous experiment, and a loud region is like a bright fringe, the soft region like a dark fringe. Using the same symbols as previously, we have the speaker separation being S, that links to the slit separation from previously. Distance from speakers to where we hear the sound, this distance would be D, which equates to the distance from slits to screen previously, and the distance from one loud sound to the next, or the fringe separation, is W. Two-source interference can also be observed with water waves in a ripple tank and with microwaves.